Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is efficiency. Our objective today is to introduce a common performance measurement known as efficiency. We'll learn to calculate efficiency for a single system or multi-stage cascaded systems. Additionally, we'll learn that output can never exceed input conditions due to inevitable losses in our system. It'd be nice, but it can't. Efficiency is a simple measure of the performance or effectiveness of a system. Given a certain input, what is the useful output obtained? It is expressed mathematically as a ratio or percentage of useful output obtained given a certain input. The formula shows output over input multiplied by 100%. I don't like percentages because I'm smart enough to figure out that 75% is 0.75 of something and so on. I just skip the percentage in the formula and do the conversion mentally. Sometimes you'll see efficiency represented by this funny looking N thing, but I would not recommend doing this because basic electronics is hard enough already. Making you remember funny symbols is just going to make you forget something else. The real world is not perfect. In the real world, things are hot and noisy, dogs vomit on your homework, and sometimes your lab partner can't figure out how to use a stairway, let alone use an ammeter. Point is, losses will always occur. These losses are peeled off from our input and are not considered useful output. If losses are peeled off from our input, it would not be too bold to presume that useful output will ever be greater than input. Therefore, efficiency will never be greater than 100%. If you ever find output greater than input, or efficiency is greater than 100%, you're doing it wrong, and you need to perform a tactical retreat and reassess your data. Given that energy can neither be created nor destroyed, but only changed in form, we can say that all incoming energy is converted into something else, and all systems are therefore 100% efficient. This is obviously not what we intend, and we must clearly delineate between useful output and losses. Depending on your perspective, one form of energy could be a useful output and in another a loss. For example, a heater produces desirable thermal output. A motor produces mechanical rotation. This is its output. However, the motor gets hot when it does so. Heat is now considered a loss because that's not the intended purpose of this motor. That is, unless you're cold. I'd suggest, though, that there are more efficient means of warming oneself besides laying on top of an overloaded induction motor. Methods like perhaps using a heater. A larger percentage of the input energy in the heater is routed to the production of heat and less to undesirable losses. It is therefore a more efficient system if your desired output is heat. If you're ever lost, just ask yourself 3 questions. What is the input? What is the output or intended purpose of the device? And what are the losses associated with its operation? Additionally, efficiency need not be limited just to the concept of energy. One could talk about power efficiency, i.e. the time rate consumption or generation of energy, force efficiency, torque efficiency, or any other desired output, including the change between like forms of energy. For example, an inverter that converts the DC electrical output of a solar array into grid-compliant AC electrical energy, or its opposite, a rectifier that converts AC electrical input into DC electrical output. Consider our motor example. A motor consumes electrical energy. That is its input. The obvious output is a physical or a mechanical movement of a shaft. Losses might include heat, noise, or other associated electrical or magnetic losses. Let's look at this motor's power efficiency, meaning the time rate conversion of electrical energy into mechanical energy. Let's say this is a 2 horsepower motor and it is consuming 1,900 watts of real electrical power. One might be tempted to just charge into a painfully obvious pit trap by plugging and chugging the numbers 2 and 1,900 into our efficiency formula. But if you do so, I promise you a painful and horrible death. The input and output conditions are both power figures, but are expressed in totally different unit systems. You've got to find a common ground between the 2 unit systems, and which system you use is of no concern to me or anyone else. Regardless, the efficiency rating should be the same. If 1 horsepower is equal to 746 watts, we need to do a unit conversion for 2 horsepower, where 2 horsepower times 1 is its watts equivalent. The one that we require is a relationship where the units we want on the top is watts, and the units we don't want on the bottom is horsepower. So 746 watts divided by 1 horsepower is 1, and our units of horsepower cancel out. We're left with 1,492 watts mechanical output. We can now use our efficiency formula, where efficiency is equal to output over input, where our output is 1492 and our input is 1900 watts, yielding us an efficiency of 0.785 or 78.5% efficient. Meaning for every watt of real electrical power that comes into this motor, only 78.5% is output as useful mechanical power. Consider the conversion between like forms of energy. For example, a gearbox, which converts rotational mechanical energy of given torque and speed values into rotational mechanical energy of different torque and speed values. The step-up gearbox in a modern horizontal axis wind turbine generator is converting the low speed, high torque rotation of the main shaft into the high speed, low torque rotation of the generator appropriate for grid synchronous generation. Losses in the gearbox might include friction and heat, noise, and backlash between the teeth. If we know the input conditions and the efficiency of the gearbox, we should be able to find the output mechanical power. Let's say we've installed a gearbox that is known to be 92% efficient. We want to determine the output of the high-speed shaft given the main shaft is rotating at 22 revolutions per minute with 825 kilonewton meters of torque. The combination of rotational speed and the twisting force known as torque is a form of rotating mechanical power. The input conditions can be found in terms of watts by using the formula speed times torque divided by 9.55. The use of this formula is featured heavily in later lectures about motors and generators. For now, don't worry about the derivation and just trust me that the mechanical power for these conditions of 22 revolutions per minute, 825 kilonewton meters of torque, is approximately 1.9 megawatts of mechanical power. If this gearbox is 92% efficient, only 92% of this 1.9 megawatt input actually gets converted into usable mechanical output power at the high-speed shaft. Therefore, it stands to conjecture that our output should be less than 1.9 megawatts. If you get more power out than you put into it, you're doing it wrong. Or you're doing it so right you need to immediately patent this gearbox, because you've created something up to this point that has been consistently proved scientifically and mathematically impossible. Regardless, a simple manipulation of our formula is now kind of a pain because the percentage measurement inside it. Again, I don't know about you, but I don't like percentage measurements and calculations because I'm smart enough to figure out that 92% is 0.92 and so on and so forth. I'll just stick with the ratio and mentally do the percentage. The choice is up to you as long as you get the right answer. Without the percentage in there, we can now manipulate the formula to solve for output, where output is now equal to efficiency times input. Again, it kind of makes sense. The input is being reduced from 100% or 1.0 down to 92% or 0.92. Regardless, the output mechanical power is 1.748 megawatts. Check your work. Is output less than input? Yes, it is. We should be reasonably confident our answer is correct. Staying with this example just a little bit longer, realize this 1.748 megawatts of output mechanical power is still mechanical power. It's just a different form of mechanical power. The gearbox took the low-speed, high-torque input of the main shaft and changed 92% of it into the high-speed, low-torque output. Let's say our high-speed shaft was now rotating at 1,854 RPM. We can now use our earlier formula for rotating mechanical power to solve for the output torque. Go ahead, I dare you to try to solve for it. You should be getting approximately 9 kilonewton meters of torque. This gearbox has a speed step-up ratio of approximately 1 to 84, and the same gearbox has just under a 92 to 1 torque reduction ratio. There's a difference between the torque and speed ratio because of the inefficiency of the gearbox. If the gearbox was truly 100% efficient, both the ratios would be the same, meaning for every proportional step down in torque, you equivalently raise the speed. This is obviously never going to happen because of the losses associated with the use of our gearbox. Realize the qualifiers high speed, low torque are only relative in nature. 9 kilonewton meters of torque is still extremely high. It'd rip your balls right out of your sockets if you grabbed the high-speed shaft, or worse yet, got a piece of your personal protective equipment caught in it. It is for this reason shafts are typically protected with safety shrouds that ideally protect maintenance personnel and operators from contact. Before we move on with the next example, consider the losses. Realize 1.9 megawatts of input has been converted into 1.748 megawatts of useful output. What happened to the missing 152 kilowatts? Has it vanished? No, this power is going towards non-useful output, namely frictional losses and sound. This is why it's so essential that a gearbox includes not just the gears, bearings, shafts, seals, and housing, but also the means of lubricating and cooling these gears. This 152 kilowatts has to go somewhere, and the film of oil coating the moving gears not only eliminates destructive metal-to-metal contact, but also transfers the heat away from the mating surfaces. It's for this reason you'll sometimes see a wind turbine with kind of this radiator thing poking up off the top of it. That's exactly what it is. It's a radiator, heat exchanger, used to cool the gearbox oil and rid itself of this heat so the oil doesn't thermally degrade and the gearbox continues to function properly. This means of cooling is especially cunning because it's almost a passive means of doing so. Think about it. When do you need to cool the oil in a wind turbine gearbox? When it's windy. The wind is turning the turbine and acting as a fan for an air-cooled heat exchanger. This is the same reason a 1970 air-cooled VW Beetle doesn't do well in a traffic jam in July. It's not moving and the heat isn't dissipated. Ask me how I know this. Moving on, consider the energy input requirements of a battery charging system that is 86% efficient. Let's say our battery or output needs to store 500 joules of energy. If only 500 joules is getting through a hoop that is 86% wide, it stands to conjecture that more than 500 joule needs to be input into this system to get the required energy output. Remember, input always has to be greater than output, and output always has to be less than input. In this case, a rearrangement of our formula using just the ratio and not the messy percentage yields input equals output over efficiency. 500 divided by 0.86. You'll find it's necessary to input approximately 581.4 joules into this system if we expect 500 joules output. The losses might include heat dissipated in the power electronics and heat produced from the chemical reactions inside the battery. Either way, that's 81.4 joules that aren't going towards the storage of electrical energy inside the battery. It's for this reason large-scale energy storage using industrial-scale batteries is still in its infancy. We'll discuss the somewhat finicky nature of batteries in later lectures, but realize there are losses associated with the charge and discharge of these devices that must be accounted for with efficiency measurements. Performing these calculations for single systems should be extremely easy. All you've got to do is figure out the input, the output, and the losses, and make sure you're using the correct units. Once you've got these figures lined up, it's just a matter of flipping your selector switch to rock and roll and engaging your target. Add to this the fact you can always check your work and make sure output never exceeds input, nor should you ever arrive at an efficiency of greater than 100%. Numbers aside, discussing efficiency and how it relates to intelligent energy is a very cool topic. Often at its most basic level, the task of engineers and technicians is to design, maintain, and improve systems so we get more output for less input. Efficiency is priority number one. Consider a community composed of shoddily constructed, uninsulated homes with extremely old, inefficient appliances. Additionally, the occupants of these houses are ugly and have a tendency to drink and fight a lot. For every kilowatt hour of energy those houses buy from the electrical utility, a large portion of it simply goes to heating the outside environment. Each individual house and the community as a whole is inefficient. If the same community wants to stay warm and comfortable in a cold environment, it will be necessary to have a large generator run for long periods of time. This is in contrast to a community of well-insulated homes with efficient appliances and whose occupants are handsome, well-educated, and reasonable. Each house and the community as a whole is efficient. For every kilowatt hour these occupants purchase from the electrical utility, more of it actually goes to heating their homes rather than the outside atmosphere. The generator can be smaller and doesn't need to be run as much. Additionally, this reasonable and handsome community makes use of renewable resources like solar thermal preheaters, photovoltaic solar arrays, and wind turbines to further reduce their dependency on black energy or the grid. Here's another non-numerical rambling about efficiency. Consider the internal combustion engine in your car. An internal combustion engine consumes gas, a form of chemical energy. The extraction of this chemical energy in some of the worst places on Earth also happens to cost the lives of young soldiers, civilians, and billions of dollars spent propping up amoral dictatorships with no affection for democracy. I haven't figured out how to account for these externalities in our mathematical relationship, but trust me, they are there. Anyways, the engine produces mechanical movement. Losses include thermal, noise, friction, and more. What if you could design a more efficient engine that extracted more output from the same input? That seems the logical place to start. Let's get crazy though, and not start with the engine, but totally, fundamentally, and radically redesign the car. Your mental image of the car undoubtedly features a four-wheel car-shaped object made out of metal. Heavy, heavy metal. The heavy metal frame is there for a reason. It's there so when a suicidal bull elk jumps out in front of you, or a trucker jacked up on goofballs decides to use your family sedan for a kickball, you'll survive the encounter. Survival is a great advantage, but it comes paired with a major disadvantage, namely inertia. Meaning that for a traditional metal-framed car, only a small portion of the energy input actually moves you and your load to its intended destination. The rest is spent moving that heavy car. Don't believe me? Put foot pedals, a crankset, and a chain on a motorcycle frame. Tell me how easy it is to take this for a foot-powered cruise around town in comparison to a regular bike frame. I'm not suggesting you to just get rid of your frame on your car and strap an engine to your butt. I am telling you, however, that we can develop a frame that's lighter and just as strong, if not stronger, than the heavy metal one by using carbon fiber, a real and present technology commercially available today, not tomorrow. Talk about a game changer. Think about a carbon fiber car that weighs a fourth of a traditional metal frame car, even half. Regardless, for the same energy input, you could carry a greater load for a greater distance. Efficiency plus, even if we're stuck with the same old gas-burning engine. Realize the carbon fiber frame is going to fundamentally change the automotive manufacturing and fuel distribution industry. There will be winners and there will be losers. If efficiency is priority one, the game has some pretty high stakes. Anyways, let's see if we could tie efficiency into our previous discussion about energy and power. If you haven't watched the Energy and Power lecture or are only vaguely familiar with its contents, I am emphatically urging you to pause this lecture and go watch it now. I'll be right here waiting for you when you get back. Consider a 100 watt incandescent light bulb, of which 97.6% of its electrical input is converted to heat and only 2.4% is converted to radiant energy. Before we delve into this example, first answer me this question. What is the intended purpose of a device which converts 97.6% of incoming electrical energy into heat? What else could you call it but a heater? Not only is an incandescent light bulb an inefficient light bulb, it is a highly efficient incandescent toaster. Here's some real figures. For every watt an incandescent bulb consumes, it outputs 16 lumens. For every watt a compact fluorescent light bulb or a CFL consumes, it outputs 64 lumens. Therefore, a 100 watt light bulb produces 1,600 lumens of light. I don't want to go into physics about light, but let's just say 1,600 lumens is 2.4 watts of radiant power. This is kind of inaccurate, but just go with it for the purposes of our discussion. Accounting for the incandescent bulb's 2.4% efficiency, we're getting 2.4 watts of radiant output, and the remaining 97.6 watts are primarily thermal losses. To get the same amount of light from a CFL, we'd only need to use a 25 watt CFL. In this case, 25 watts of electrical input is being converted into 2.4 watts of radiant output. What's the efficiency of a CFL? Using our formula for efficiency, where efficiency is output over input, and substituting in the appropriate numbers, 2.4 watts divided by 25 watts, a CFL is only 9.6% efficient. Surprising, eh? You'd think it'd be better, but it isn't. However, in comparison to an incandescent, who cares? It's still 4 times as efficient. Consider the energy and cost savings of these two different technologies with markedly different efficiency ratings used for the same purpose. Let's say the Happy Cat cat food factory requires 160,000 lumens to light up its factory floor for 12 hours a day. You could use 100 watt incandescents or 125 watt CFLs. Either way, you're getting the same amount of light output, namely 1,600 lumens each, or 160,000 lumens altogether. It's just that the incandescents are requiring more input because they're inefficient in comparison. Consider the annual energy requirements and costs for these two configurations. Let's say the cost of electricity is 13 cents per kilowatt hour. Pause the lecture and see if you can determine the daily and annual energy requirements and the annual cost for these two different configurations, and finally determine the cost savings between them. If we used 100 watt bulbs for 12 hours a day, we'd be consuming 120,000 watt hours per day, or 120 kilowatt hours a day. If we consumed 120 kilowatt hours a day for 365 days, or a whole year, annually we'd expect to consume 43,800 kilowatt hours of energy annually. You could also call this 43.8 megawatt hours. However, since we're sticking with the units of kilowatt hours for cost, don't do this. For consuming 43,800 kilowatt hours, and we're being charged 13 cents per kilowatt hour, our total annual costs will be $5,694 for the use of 100 100-watt incandescents. We'll stick those figures over there. Let's do the same thing for the 125-watt CFLs. If we use 125-watt CFLs for 12 hours a day, the factory's lighting load would be 30 kilowatt hours daily. If you consumed 30 kilowatt hours every day for 365 days, or for an entire year, you'd be consuming 10,950 kilowatt hours annually, or 10.95 megawatt hours if you wanted to use the appropriate engineering prefix. I wouldn't do that though, because the unit for cost is kilowatt hours. What we're going to do is take 10,950 kilowatt hours times 13 cents per kilowatt hour, yielding us a total annual cost of $1,423.50 for the use of 100 CFLs. We'll put those figures over there and take both configurations into consideration. The switch from incandescents to CFLs would yield us an annual cost savings of $4,270.50 just by switching out the light bulbs. In an era of increasing manufacturing competitiveness and surrounded by countries willing to use nothing short of slave labor, we can simply not afford to be stupid anymore. Add to this the annual cost savings benefit, the fact that a typical CFL has a lifespan 8 to 10 times that of a typical incandescent. There are gullible jerks out there quick to seize upon the disadvantages of CFLs, just because some windbag on the radio sold them a story about jackbooted government thugs breaking down doors to steal guns and light bulbs and forcing you to gay marry a vegetarian. Yes, CFL light bulbs are more complex to manufacture and require special disposal procedures. I'm not saying they don't. I'm saying they use less energy because they're more efficient than a device invented in the late 1800s when horses carried children to their jobs in the coal mines. They're more complicated for a reason. As long as you dispose of them properly, and for crying out loud, don't eat them, the CFL is a sure bet. Sticking with the Happy Cat cat food factory for one more example, let's reconsider our first motor example. If we remember correctly, our first motor example had an efficiency rating of 78.5%. It converted 1,900 watts electrical input into 1,492 watts mechanical output. This 78.5% efficiency rating, it's an okay efficiency rating for an electrical motor. Believe me, I've seen worse. But believe me, we can do better. An efficient cat food factory does not run by light bulbs alone. Consider the collection of 2 horsepower motors used to grind up old gym mats and baby harp seals into cat food. See if you can calculate the energy consumption and cost of running a motor over the course of a 40-hour work week for 52 full weeks. Let's assume the price of electricity went up and it's 15 cents per kilowatt hour now. Okay, remember, energy is power times time. 1,900 watts used for 40 hours is 76 kilowatt hours of energy for that 40-hour work week. If there were 52 work weeks within a year, annually we'd expect to use 3,952 kilowatt hours. If we're being charged 15 cents per kilowatt hour, 3,952 kilowatt hours will be $592.80. Consider the cost and energy savings if you stepped up to a 91% efficient motor. This 91% is not by any means inconceivable. That same 2 horsepower output, or 1,492 watt output, can be realized from a smaller input. In this case, we have an output and an efficiency rating, and we need to solve for input, where input is equal to our output divided by our efficiency. Meaning this same 1492 watt output could be realized from a 1,639 watt input if we use the more efficient motor. Now, solving for our energy use, we realize that energy is power times time. 1639 watts used for 40 hours a week yields 65.5 kilowatt hours for that work week. If we did 52 work weeks for a year, annually we'd consume 3,409 kilowatt hours. If we were charged 15 cents per kilowatt hour, 3,409 kilowatt hours would annually cost us $511.35. In this case, we saved $81.45 in energy costs over the course of a year just by using a slightly more efficient motor. Keep in mind this figure was just for a single motor. If you used 100 of these motors, you save 100 times this figure, or $8,145 in annual energy costs. You might think we've choked the efficiency topic into submission by now, but wait, there's more. We've yet to talk about the efficiency of multi-stage systems and renewable resources. Luckily, these topics are low-hanging fruit when you've got all the previous material in this lecture behind us. Consider a complex system, like a factory, a car, or a turbine. Despite its complex nature, realize even the most complicated system can be broken down into smaller and smaller and simpler subsystems, each with its own independent efficiency rating. There exists within this complicated system an unbroken linear chain where the output of one simple system is being fed into the next. Consider our earlier battery charging system example. In that example, we used a battery charger that was 86% efficient and converted 581.4 joules of input electrical energy into 500 joules of stored chemical energy. If this stored chemical energy was to be withdrawn from a battery in order to run a motor, consider the following scenario. Let's assume the discharge process itself has an efficiency rating of 90%, meaning only 90% of those 500 joules stored in our battery could be withdrawn. Let's say that discharge stage is being fed to a brushless DC motor. The brushless DC motor has some power electronics intermediary between it and the actual motor. These power electronics have an efficiency rating of 98%. Finally, the power electronics feed the motor. The motor itself has an efficiency rating of 88%. What you'll realize is that the initial 581.4 joules of input is just going to get reduced and reduced and reduced every time it passes through one stage and is handed off to the next element in the series. If you ever played the game telephone before, you realize your output will suffer cumulative losses with increasing number of stages, and the efficiency rating for the complete system can never be greater than the least efficient stage. If it helps you understand cascaded efficiencies, use the visualization that each subsystem represents a window that is progressively narrower as you go from one level to the next. At each point, a portion of that stage's input is shaved off and lost to the following stages. What you'll find is that though each stage may be individually efficient, the whole system's efficiency is substantially less efficient than the least efficient stage. This really drives home the importance of maintenance of critical subsystems in power generation facilities and factories, and the proverb that no chain is stronger than its weakest link. In this battery motor system, we've got a chain represented by the charge, discharge, power electronics, and motor. If our initial 581.4 joules gets whittled down by 86% efficient charging stage to 500 joules, only 500 joules of energy is available to discharge. The 90% efficient discharge process takes 500 joules and converts it into 450 joules, which is then handed off to the power electronics. The power electronics themselves have a respectable efficiency rating of 98%. However, realize they only got 450 joules handed to them because the charge and discharge stage dropped a couple joules along the way. The 98% efficient power electronic stage takes 450 joules and whittles it down to 441 joules. Finally, the power electronic stage hands off these 441 joules to the motor, and the motor just drops 12% of these joules on the floor because it's only 88% efficient. Therefore, only 388.1 joules of useful mechanical energy is output to our system. See how the output gets progressively smaller and smaller as it passes from one stage to the next. If you step back and look at the system as a whole, realize 581.4 joules went into our system and only 388.1 joules came out of it. If you think on a system level, this whole system would have an efficiency rating, where the system efficiency is 388.1 joules divided by 581.4 joules, or is therefore 66.8% efficient. What's crazy about the system level efficiency figure is that it is the product of all individual efficiency ratings for the individual stages that make up the complete system. Don't believe me? Check my work. 86% times 90% times 98% times 88% is equal to 66.8%. This is a great shortcut if you've got a chain of systems and you know each individual system's efficiency rating. It's very easy to determine the system level efficiency simply by multiplying each stage's efficiencies together. Notice, despite no individual system having an efficiency rating of less than, in this case, our charging stage at 86%, the entire system's efficiency rating is still much less than this lowest efficiency rating. This is always true. If you find a whole system efficiency rating larger than any individual stage, you're doing it wrong. Again, no chain is stronger than its weakest link. Let's try an efficiency example using a wind turbine. A wind turbine as a whole converts the mechanical power of a column of moving air into electrical power output. Some people think they're fans. Some people think they mill grains. They are not cow coolers. They are not windmills. They're wind turbines. They make electricity. Tell people about this. Spread the word. There seems to be some major confusion about this in the general populace. Anyways, in this case, we're going to model the wind turbine as a set of stage subsystems, where each subsystem has an efficiency measurement. Our cascaded system consists of a rotor, the main shaft, the gearbox, the generator, high-speed shaft combination, the power electronics, and finally the transformer. I've already got the figures written out here, but just play along as we go through this example. The power in a column of wind is proportional to that wind's density, the cube of its velocity, and the area of the column. Denser air, let's say humid air next to a body of water, more power. Bigger diameter means squared bigger area, more power. Faster wind, lots more power, because it's cubic in nature. This simple equation answers two questions people often have about wind turbines. Why are wind turbines so big? The larger rotor swept area increases the amount of wind it intercepts. Why are they so tall? The tall towers expose them to faster winds unobstructed by cows, people, and trees. Given the following conditions, where the air density is 1.25 kilograms per meter cubed, the wind speed is 12 meters per second, and the diameter of our turbine is 77 meters, determine the mechanical power input to our wind turbine. In this case, a diameter of 77 meters means we have an area of pi over 4d squared, which means we have an area of 4,657 meters squared. The mechanical power in our moving column of wind is just over 5 megawatts of power. This roughly 5 megawatt input, however, is subjected to the most critical of efficiency measurements regarding wind power, the Betz limit. The Betz limit is the theoretical maximum of roughly 59% that can be extracted from a column of wind, beyond which the wind would just stop moving. Even well-designed modern wind turbines have not even come close to the Betz limit. A respectable modern wind turbine might be capable of extracting only 40% of this oncoming wind power and converting it to useful rotational mechanical energy. This is the job of the rotor subsystem, consisting of the blades and the hub. In this case, it's got a 40% efficiency rating, meaning it's taking that roughly 5 megawatt input and converting it into roughly 2 megawatt output. This roughly 2 megawatt output is now the input for the main shaft, also called the low-speed shaft, which represents another subsystem with an efficiency measurement of 96%. This efficiency measurement accounts for frictional losses in the bearings. This 2 megawatt input is converted into roughly 1.9 megawatt output. This 1.9 megawatt output of our main shaft is now the input for our gearbox, which has a 96% efficiency rating. In this case, it's accounting for the frictional losses, heat, backlash, and noise. This 1.9 megawatt input gets whittled down to roughly 1.8 megawatt output, which is now being fed to our generator high-speed shaft combination. This generator high-speed shaft combination also has an efficiency rating of 96%, taking into account for misalignment between the high-speed shaft and the coupling, perhaps friction and heat. This 1.8 megawatt input is reduced to a 1.78 megawatt output. This 1.78 megawatt output is fed to the power electronics with a 96% efficiency rating, accounting for any heat or electrical losses, which reduces it to 1.7 megawatt output. This 1.7 megawatt output is being fed to a transformer also with a 96% efficiency, accounting for any heat, magnetic, or electrical losses, yielding us a final output of roughly 1.64 megawatts. Though each stage, with the exception of the rotor at 40%, is a respectable 96% efficient, the whole system actually converts only 1.6 megawatts of the available 5 megawatts of wind power to usable power. On a system level perspective, the wind turbine is therefore only 32.6% efficient, showing us the cascaded efficiency of a system is always lower than the least efficient part. The least efficient part being the rotor at 40%, or less than that, and I suspect our answer is correct. This 32.6% efficiency number is something the gullible jerks of the world are quick to seize upon as a clear indication of wind power's inefficiency. My response is to compare this with the truly inefficient nature of capturing a dinosaur, killing it, burying it in a swamp, and sitting back for a long time while you wait for it to turn into a distillable petroleum product. Add to this cascaded system the inefficiency of the extraction process in a region not exactly known for its political stability. You get my point. The weak link in our turbine is the real practical limitation imposed on the rotor by the Betz limit. If you simply say, okay, I'm defining my system as the rotor on back, you could say roughly 1.6 megawatts of useful power was produced from roughly 2 megawatts of mechanical input. You could then say your system is 81.5% efficient. Additionally, you could just say each subsystem from the rotor on back is 96% efficient and just print that in bold letters and let the customer figure it out for themselves. Again, to arrive at system efficiency directly, we could also take the product of each individual stage to arrive at system efficiency, where 40% times 96% times 96% times 96% times 96% times 96% yields 32.6%. If roughly 5 megawatts of input came into a system of 32.6% efficiency, it'd yield roughly 1.64 megawatts output. Be aware there are systems and occasions with more than one input and more than one useful output. Consider a geothermal plant, where there's a quantity of geothermal energy inside the earth that needs energy to be extracted. In this case, there'd be 2 inputs. It could also have 2 outputs, where we produce electricity and usable heat. In this case, it would have 2 different efficiency ratings. One for the conversion of all input into electricity via a steam-driven turbine, and one for the conversion of all input into useful heat energy. This thermal energy could be used to warm buildings, water, or dry agricultural products. Geothermal plants are pretty cool because they do require initial startup input to run pumps and other ancillary devices for the extraction process. However, once the turbine is actually producing electricity, this geothermally produced electricity can now run the plant. Point of clarification about this: you are not getting anything for free. The source of energy is still geothermal in nature, and due to inefficiencies, the quantity of electrical and heat energy exported is still less than the huge geothermal input supply to the whole system. It's just that you don't require external input to extract the geothermal energy once the turbine's running. For a geothermal plant to be commercially viable, the quantity of exportable energy needs to be greater than the amount necessary to extract it. Let's close out this lecture on efficiency with a quick discussion about renewable resources. Wind turbines are theoretically limited to the Betz limit, roughly 59% efficiency. Not a single wind turbine on Earth has gotten even close to this limit. Therefore, we are operating at efficiencies less than 58%. And it's definitely less than this because we've got all those cascaded subsystems in there. It's a definite F. Solar panels are even worse. Even the highest performance solar panel commercially available only reaches an efficiency of around 20%. Meaning for every 1,000 watts per meter square reaching the solar panel, only 200 watts gets converted into usable DC electrical output. This 20% efficiency rating is not even enough to register on the F- scale. Efficiency fail. For some reason, the demonstrable declaration of inefficiency rubs people the wrong way. Yes, these technologies are inefficient, but my follow-up to this point is, who cares? Those with only a superfluous knowledge of reality, or perhaps a truly twisted political agenda to pursue, can ignore what is happening to the excess wind or sun or water. Is it leaking all over your roof, spilling over your yard, and seeping its way into your aquifer? Oh no, your well is contaminated with sunlight. Does the pursuit of scarce wind resources in third world countries require you to prop up morally questionable dictatorships with the combined might of an expensive military campaign and the lives of young men and women? No, it's renewable. It's everywhere, it's abundant, and it's absolutely free. Consider a gasoline-fueled internal combustion engine. The efficiency might be better than a solar panel, but discussions of efficiency aside, you've got to buy the fuel. When you run out of gas, the sun is still going to rise. Besides the initial expense and periodic maintenance of renewable energy, the fuel costs you nothing. You have to buy an internal combustion engine. You have to maintain it, and you have to buy the fuel. You have to buy a turbine, you have to maintain it, but the fuel is free. This is the magic bullet that stops your crazy uncle in his tracks when he's running his mouth at the Thanksgiving table. Draw a graph of fuel prices as a function of time. The price of gasoline has done nothing but rise. The price of renewables has done nothing but fall. Can you dig it now? Your uncle will shut his mouth and you can get back to that third helping of turkey. Returning to our topic of efficiency and renewable energy being the inefficient beast it is, designers need to care about the efficiency rating of elements in our system that precede and follow the initial conversion of a renewable resource into something usable. Once you've extracted a quantity of energy from a limitless resource like the sun or wind, regardless of how efficient this first step is, you need to carefully and gently pass it from stage to stage and not spill a drop of it along the way because of the cascaded nature of your system. Truly, the only challenge preventing the widespread adoption of renewable energy is not the efficient extraction of a limitless and abundant resource, but the cheap production of a device that allows you to do so. Alright, we need to wrap this up and send you back to the real world feeling like you've learned something. In conclusion, this lecture presented the concept of efficiency, and we learned to calculate efficiency, input, or output. Additionally, we discussed cascaded efficiency arrangements and renewable resources. We learned that the efficiency of a cascaded system is a product of individual stage efficiency ratings and is always less than the least most efficient system. Finally, we learned that no system can ever produce output greater than its input, and we use this fact to check our work. You should be able to pick up this concept and run with it. Remember to review this material as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your Lazy Lab partner about this resource, and be sure to check out the Big Bad Tech playlist for additional resources and updates.